Very well. So I'm Gaetano. I am a research associate at the UNSW Canberra. Our focus is, as the slide is saying, hypersonic fluid structural interactions. Our focus, most importantly, actually, is the hypersonic flight. So hypersonic means every vehicle that is flying at a speed that is several times the speed of sound. Okay. So, for example, this SR-72 is designed actually to reach Mach 6. So something like 7,000 kilometers an hour, right? So at this speed, the heat loads on the skin panels is extremely high. And depending on the substrate that you have underneath, it can result in this very ugly thermal distribution, but most importantly, also in mechanical properties degradation. So the skin panels of the, let's say the young modulus of the skin panels of the hypersonic vehicles will start degrading. So the young modulus is going down. Additionally, these vehicles don't like to fly, and the engines doesn't produce enough thrust. So you have a vehicle that doesn't produce enough lift, doesn't produce enough thrust, because ramjets and scramjets are clearly much less efficient than airliners. Otherwise, we'd be using scramjet at the ground. And so you have to make these models extremely light, right? So skin panels that are light and heat loading results in structures that are easy to vibrate, fatigue, and undergoing dynamic instability, flutter, etc., etc. So this is what we are doing in UNSW Canberra, and we are leading this at the moment. But we are also collaborating with the University of Southern Queensland and the University of Queensland. Most particularly, we are doing experiment in a wind tunnel, in a Mach 6 wind tunnel, is capable of reproducing a free jet, Mach 6 free jet, for a very long time, approximately 200 milliseconds. You say, it's actually a very short time. Well, no, because compared to typical Australian shock tunnels, the test time is actually 1 millisecond. So in this tunnel, you can actually reach something about 200 times more. So now, the case that I'm showing to you today is what happens when these vehicles start oscillating. So you have a shock from the leading edge that is oscillating inside the cone. It can create, it can actually deteriorate the propulsive efficiency of this vehicle. It is already very low. Additionally, on the top of that, put the structural deformations, for example. You know, this vehicle was 3.7 meters long. NASP was a large scale of these, which is about 30 meters long. And you know, 1% deformation, 2% deformation on that scale is something possible. Right? So we want to check what is the effect on the wall of the oscillating shocks. So we did this experiment in tunnel where we designed a very, very, very light wedge. It was almost empty. And we pivoted, it to a point here. You can see here the main flange of the tunnel, and the nozzle, and the Mach 6 core flow exiting the nozzle, producing oscillations. So the oscillating shock generator here, this wedge, will oscillate in the flow because of the action, because of the pressure resulting from the flow. Many universities trying to do this one by actuating directly the wedge, and they didn't succeed. So I had the idea of why don't we actually make it moving passively. This means that you have to have at least, let's say, 10 oscillations in 0.2 milliseconds. Sorry, in 0.2 seconds. Did it work? Yeah, it worked. So in this video, you can see a shock that is changing impingement point with time, and every time the shock is impinging on the surface, creating a bubble. Now, the region just downstream this bubble is very important. It's called reattachment. And it's characterized by very high peak heating and peak pressure. It's very important to model that part. And at the moment, our numerical capabilities are saying that we are actually able to get that. But this is a 2D numerical simulation. Our focus actually is boundary layer transition. So just downstream, the shock impinging, just downstream the bubble, I had something very strange. My pressure measurements said that there was a big plateau here, while in reality my numerical simulation said there was a peak. And actually checking my pressure distribution, we got that in that region actually is not a plateau. There are two distinct peaks. It seems to be the signature of boundary layer transition. And boundary layer transition is very related to the presence of these very beautiful vortices. They are called Bortle vortices. So in few words, what we are going to do very soon is something like, FSI simulations are very expensive. So we are going to not only do three-dimensional FSI simulations, but eventually we want to use LES to characterize these regions here and then try to model the transitions. So I have limited time today. So what I want to tell you that at the moment we are also doing some experiments where we have different elements that are moving just to characterize different time scale representing of the vehicle. So for example, this wedge could be representative of the vehicle changing altitude and inclinations, while this, the plate underneath could be representative of the structural deformation taking place within the vehicle. And so, it's about it, it's my presentation. Thank you so much.